Okay, so looking at gas stoichiometry, what we're going to be dealing with today is this is a method of predicting or analyzing the quantity of gas involved. So anytime I'm dealing with a gas, I can figure out mass, but more likely what we're going to be figuring out if we're talking about a gas is what? Anybody know? The volume of it, right. And so gas stoichiometry means I'm going to be dealing with this PV equals nRT. And we have to go back and remember everything from the gas law unit in order to be able to do our stoichiometric calculations that involve gases. And so PV equals nRT is the ideal gas law. In order to use the ideal gas law, pressure has to be in what unit? Kilopascals, right? So this has to be in kilopascals. The volume has to be in liters. N is what we always call, so it's going to be moles. R is that constant of 8.314, and that would be 8.314 kilopascals times liters divided by moles and kelvins, right? And because the unit works that way, they have to all be in those appropriate units in order to cancel out and for me to be able to solve for that unknown. Thank you. No, we're good. Okay, so 8.314, it's just a constant, right? It doesn't change. And the last one is temperature in what? Kelvin, right? So remember, anytime we're dealing with temperature here, in gas stoichiometry, temperature has to be in Kelvin. And you also, I guess, then have to remember how to convert from degrees Celsius to Kelvin. What do I do? Yeah, so to go from, if I have 20 degrees Celsius, is that, right, so that means I have to add 273.15 Kelvin. So that would be 293.15 Kelvin is 20 degrees Celsius. To work backwards, I would be subtracting that number if I come backwards. That can go in the garbage. You wrote this, so just put it in the garbage. Thanks. Okay, so everybody's good. I'm probably going to erase that. My next thing pops up. We're good? Okay. So that's just what that's saying. So we're using the ideal gas law to perform calculations. I guess I should say in conjunction with PV equals nRT, even in the gas law unit, I used what formula? Because I could say, well, you know, a canister of, or like, if oxygen weighs 25 grams, I can still ask you to go figure out the volume at SATP. So what formula would I need to use in conjunction with PV equals nRT to answer that question I just asked? Right, so I can always kind of use N equals M over M, which also means in my gas law stoichiometric calculations, I might need to use that depending on what they give me in the question. Garbage. Alright, so let's go look at some questions. Really, the process for stoichiometry is going to be exactly the same, so let's just kind of do a quick refresher on our steps. So obviously we have to read the problem. Once I've read the problem, I need to do what? Pardon? Once I've read the question? Pardon me? Givens? Well, but if I don't have an equation, what do I... Right, so the first thing I should do is write out that chemical reaction, the balanced chemical reaction, and write my givens underneath it. My givens should then give me an indication as to what I'm going to go solve moles for, so I'll solve moles for next. Once I have the moles of a compound or element, I then do what? Nope, can't remember. Once I have moles and I need to go find out something, some other unknown of a different compound or element, what do I need to do? Multiply by my molar ratio, yeah, and then the last thing would just be to find the unknown. So here's this example. If 300 grams of propane burns in a gas barbecue, what volume of oxygen is measured at SATP? Measured at SATP is required for the reaction. So first thing I need to do, go write out the balanced equation. propane is something you should know, one of those chemical formulas you should know, and that would you would know that from the first unit, chemical bonding. How many carbons? 3C3. Oh goodness, this doesn't like me. H8, right? Double plus 2 for that alkane is going to react with oxygen, which is diatomic when it's by itself. So it's a gas. And so this is a combustion reaction. What would I be producing? Pardon? Carbon dioxide, right? CO2 gas. And water also as a gas. We talked about that yesterday, right? Water has to be a gas there. It's not, a fire is not creating liquid water. Okay, so then I need to balance it. So 3 carbons, 3 carbons. I always leave oxygen last in a combustion reaction. And so 3 carbons, 3 carbons. I have 8 hydrogens, so I put a 4 over here. So that gives me 8 hydrogens. That's good. My total number of oxygens is going to be 3 times 2 is 6, plus the 4 from the water is going to give me 10 on the product side. And that means that if I put a 5 here, this reaction will be balanced. And I should always go through and double check my balancing. If I don't get my balancing right, that means you won't get your molar ratio right, and there's no possible way for you to get the right answer if you don't have the correct molar ratio. Okay, so then I'll write what I know underneath all of these pieces of information. So they're telling me that 300 grams of propane is burned, so I'm just going to do propane here in orange. So the mass of propane is 300 grams. And then I'll do oxygen here. They're looking for what is the volume of oxygen. And so when I look at this, I already know what 2 formulas I'm going to have to use and where. For propane, what formula am I going to have to use? N equals M over M. And what am I looking for in this formula? Moles, right. And so I'll find the moles by putting 300 grams in here. I'd have to figure out the molar mass of propane, which I believe is 44.11. 12.01 times 3 plus 8.08. Yeah, 44.11. And divide those, so 300 divided by that molar mass of propane, which gives me 6.80, blah, blah, blah. Keep that trailing decimal, moles. And so I figure out the moles of propane that have reacted if I burnt all 300 grams. But now what? PV equals nRT. Can I just jump right into PV equals nRT? What do I need to do? I think perfect description, actually. The molar ratio, right, yeah. So we're going to take this times by where I'm going to. So I'm going to the coefficient of 5, divide by where I'm coming from, so the coefficient there is 1. So the number of moles of oxygen that react here are, so I just times that by 5, the number of moles of oxygen are 34.0, and there's some decimals back here, so moles. And so I have N and V, and they're looking for the volume of a gas, right? I mean, some people maybe might get confused and say, well, I could use C equals N over V here. I can only do that if I have a concentration. We're talking about a volume of a gas, so we have to use PV equals nRT. Now, where am I getting the additional information in order to go into PV equals nRT from? SATP, right? And remember, SATP and STP are standard values. They're in your data booklet for you. And so the pressure at SATP is 100 kilopascals. I'm trying to figure out the volume of oxygen that reacts in that 34 moles. R is the constant of 8.314 times by the temperature, which I would have to convert to Kelvin. So temperature at SATP is 25 degrees Celsius, so that's 298.15 degrees, or Kelvin, pardon me. 298.15 Kelvin. So multiply that all together. that trailing decimal, 34, times by 8.314, times it by the 25 degrees Celsius, which is 298.15 Kelvin, just in one spot is fine, yeah. 15, and then I'd have to take all of that and just divide it by 100. So the volume of oxygen gas that would be required in order to burn off that 300 grams is going to be, divide that by 100, sorry, 843 sig digs, 842.9, so it would be 843 liters. Quite a large amount of oxygen in order to burn off that 300. The thing to know about like these stoichiometric calculations is generally when we do a reaction, one of them is going to be in limiting and one of them is going to be in excess. Just to make sure everything kind of reacts. One of them would be completely used up and one of them would probably still be left over. These values are if they both completely reacted and there was nothing else left. Right there. All right. I'll do one more, and then you guys are going to do one more. Have you seen that video? It's actually pretty sweet. No, he takes a big hunk of sodium and chucks it in the river. Yeah, but francium is so, like, to even get francium, it's so volatile. Like, it's hard to even get cesium. Yeah, it's hard to even get cesium. Alright, anyways. So, hydrogen gas is produced when sodium metal is added to water. What mass of sodium is necessary to produce 22 liters of hydrogen at SATP? Alright, so let's give myself a little bit more room. So first step, again, we got to write out this balance reaction. So hydrogen gas is being produced. So that means hydrogen is going to be a reactant or a product. A product, so this is going to be H2 gas. Is produced when sodium metal, so that's just like a big hunk of sodium. Sodium metal is added to water. I'm going to write water like this. It's easier to see what happens then. And that's why we get the explosion, right? As soon as I put the sodium in the water, there's hydrogen there, and the hydrogen will react with the air to get that explosion. Technically just creating more water. So what happens here is the sodium is reacting with the water, and there's a whole bunch of the waters in there, right? So one of them would dissociate to become this guy, and the other one stays together as the hydroxide ion and is going to join on to give me sodium hydroxide, NaOH, which is aqueous. And then I would need to go balance this. So there's two hydrogens. I need to put a 2 in front of here, a 2 in front of here. Come on, get in there. And a 2 in front of here. So two sodiums, that's good. Two hydrogens, that's good. Two hydroxides, I'm balanced. So then I'll take the information that I know and put it underneath each compound here. So hydrogen gas is produced. What mass of sodium, so I'm trying to figure out the mass of sodium here, is required to produce 22 liters. So the volume here is going to be 22 liters at SATP. And so SATP is just the way of them indirectly giving me pressure and temperature without saying a whole bunch of details. Alright, so I'm going to go do hydrogen, yellow. So first thing I need to do once I've done this, write everything, I got to go find moles. Can I find what substance can I find moles for? Hydrogen, right. And so I'll go find moles of hydrogen using what formula? PV equals nRT. So PV equals nRT. The pressure based off of that SATP condition is 100 kilopascals. The volume they just told me that reacts is 22 liters, not moles. I'm trying to figure out moles. R is the constant of 8.314, and the temperature is 25 degrees Celsius, so it's 298.15 Kelvin. And so to solve this, I'm just going to divide this off, 8.314 times 298.15. And I'll divide it from this side as well. So 8.3, this thing is too small, 8.314 times 298.15. And so 100 times 22, and divide that by 8.314 times 298.15. Make sure if you did that all together, you put brackets around your numerator, brackets around your denominator. Otherwise, your calculator will just go through BEDMAS in a linear fashion. And so the number of moles then in that 22 liters of hydrogen is 0.887, and that decimal continues, moles. So then I need to go figure out the moles of sodium by using my molar ratio. So I'll times by what? 2 over 1, right? Times by where I'm going to. I'm going to sodium, so it has coefficient of 2. Divide by where I'm coming from. I came from hydrogen, which had a coefficient of an invisible 1 right there. So I'll double the moles, which tells me that this is 1.77. Again, I want to keep that trailing decimal in. And so then I'll take that information and substitute it into n equals m over m. So the number of moles is 1.77, blah, blah, blah. I'm looking for the mass in the molar mass of sodium, which is 22.99. Yeah. 22.99. And so I'll just cross multiply. And the mass of sodium that would react in order to get that 22 liters of hydrogen gas with proper sig digs as 3 sig digs is 40.8 grams. Just a massive piece of sodium. And then they'd have to harvest that hydrogen somehow. Mm-hmm. Yeah. How's everybody feel about that? Okay, not too much different from yesterday. Everybody thinks they can manage. Okay. There was one more question on there. Do you feel like you need to do it, or are you okay just to jump into the homework questions? Everybody's okay? What's that? Jump into the homework? Okay, cool. All right, so this is probably definitely not the right homework, is it? Yeah, homework 5. I printed out the answers for the homework, so they are in the homework books. They're also posted on Google Classroom if you need to go consult to check anything. So homework 5, you should be able to do every single question in there. How many questions? There's only like 5 questions, right? 5 or 6? 7? Okay, I lied. There's 7. But... All right.